I'll start with a bit about me. So I graduated from James Bruce this year, and the subjects that I took were English Advanced, Mathematics Extension 2, Physics, Chemistry, and Science Extension. And I think from taking Science Extension, I've learned about a lot of the working scientifically skills in a lot more at a higher level. So I will be incorporating that into the courses that I teach. And like Karui, I have participated in the Olympiads quite a lot. And once again, I won't speak too much about my journey, but it's much similar to his. And I represented Australia at the International Chemistry Olympiad in 2021 and in the Physics Olympiad this year. And I achieved a bronze medal at both of those competitions. So now I'll share with you some of what I've learned along the way and how I think you should approach studying physics. I think a lot of people find physics quite frustrating because some of the concepts that you cover might be quite difficult to understand and you might not consider them that intuitive. As a result, I think it's very important that you find ways to motivate yourself so that you can persevere and ultimately improve in the subject. Students can really foster their interest in physics by linking the physics principles that they learn to real-world physics and just like the cutting-edge physics research and even things in your everyday lives. So here I have two of the cutting-edge, I guess you could call them the frontiers of physics at the moment. So on the left, I have an image of LIGO, and basically what that is, it is a device that measures very, very small contractions in space. And then by doing that, we're able to deduce information about really high energy astrophysical events. So things like black hole mergers. And on the right, you've probably heard about quantum computers before, but they are just computers which harness the phenomena of quantum mechanics. And as a result, it's hoped that larger ones will be able to solve problems quicker than classical computers can. And the reason why I've included both of these examples is that whilst the physics that is involved in these things might be well beyond what you would learn at a high school level, a lot of the things that you do learn in high school are applied to these sorts of projects. So for example, in the case of LIGO, what is actually detecting is things called gravitational waves. And waves are something that you learn about in year 11 in the Olympiad course. And that device there is also what we call an interferometer. And that is something that you will learn about in year 12. And in terms of quantum computing, the actual computers themselves have many electrical circuits, and electric circuits are something that you'll see in year 11 and in the Olympiad course. And the entire computer is based on the principle of the quantum mechanical nature of the atom, which is something that you will see in year 12. So I think this sort of echoes what Karui was saying before about building a foundation, then applying your knowledge. But likewise, I think that in order to succeed in physics, you need to first you need to be confident in your theoretical knowledge. And then once you do that, then you need to develop your problem solving skills. And if you only have one of these, then I think it's very important that you need to make sure that you develop both of them in order to succeed and maximize your marks. So in terms of what that would look like, in terms of consolidating theoretical knowledge, you should be doing things like reviewing your class notes or your textbook and clarifying any unclear points by asking questions. And this is where the fact that our course is accelerated helps, because since you've already seen the content before, when you're in school, you will know what are the good questions to ask to further your understanding. And finally, in terms of helping you retain knowledge, I think you should quiz yourself. And what that could look like is maybe you could pair up with someone and ask each other questions. You could use flashcards and test yourself, or you could just simply go through the syllabus and look at each point and see whether you've addressed it and can answer it, I guess. And in order to develop your problem solving skills, I think it's very important that you do past questions. So in the case of the HSC, you could be looking at past trial exams. The trial is essentially an exam that you sit at the end of year 3, early term 3, which is meant to resemble the HSC exam. And of course, you could look at the past HSC exams as well if you're studying for the HSC. They're obviously going to be the best indicator of what you're likely to see. And for the ASOEs, the Olympiads, I think you should be looking at past papers for that competition. And if you want even more resources, then you could be looking at Olympiad exams from other countries. However, in my experience, I found that a lot of the exams from the other countries are at a high level. So if you find those very difficult and harder than what you see in the enrichment course at Toplogic, then it is understandable, and it's probably just because those competitions require a greater theoretical foundation. You can also look at textbook questions, and one textbook I recommend for physics is Giancoli. And in terms of doing questions, I think it's very important that you check your answers, because if you don't, then you don't know whether you've applied your physics concepts correctly. And I guess the same goes for chemistry. And yeah, so it's very important that you check your answers to make sure that your study is actually efficient, because if you're not getting the right answers, then you have something wrong with your theoretical knowledge, which you should be addressing ASAP. Because if you don't address that, then there's not really any point in practicing your problem-solving skills. So like what Karui said, working scientifically is a very underlooked portion of the HSC course. And I guess it's also very important for the Olympiad as well. So what working scientifically is that it is a set of skills that you need to acquire scientific knowledge. So it is what people, when they're actually doing science, like in the projects I showed you before, they are actively employing their working scientifically skills by doing things like questioning. They are planning investigations and actually conducting them. They're doing data analysis. They need to communicate their results. They need to solve problems. So it's very important that since physics and chemistry aren't sciences, like you need to be able to work scientifically and have like the skills needed for you to develop knowledge in those sorts of fields. It's very important on a practical sense, because working scientifically can be assessed for 60% of your school-based assessment. So that's more than the proportion for knowledge and understanding. And within this component, that includes the depth study, which is where your school will assign you a task, and you need to essentially use your working scientifically skills to increase your knowledge and understanding and extend it beyond what is in the syllabus for one dot point. And working scientifically also appears throughout the HSC. We don't have a given percentage, but it's integrated throughout all the questions. So you might have a question where they give you a stimulus and you need to process the data from it. That would count as working scientifically. And such a question might also require you to use your knowledge and understanding from the course. So as you can see, working scientifically is everywhere, really. So it's very important that you address that. And as a result, at Toplogic, what we'll be doing is we have a dedicated working scientifically course at the lesson at the start of the year 11 course, to make sure that you understand what is required for each of these 7 outcomes. And we'll also make sure that students can develop these skills throughout the course by making sure that there are questions testing these skills all throughout all the homeworks. And working scientifically is also embedded within the course content, because some of the dot points, at least for physics, require you to do first-hand investigations. And whilst it might not always be possible due to equipment constraints and the fact that some of our lessons will be online, we will be endeavoring to supplement those sorts of experiences with simulations where possible, and that will enable students to further develop their working scientifically skills. So as I said before, problem solving is one of the working scientifically skills. So it is very important that you enhance your ability in this area. So in physics, generally problem solving skills are about knowing which formula or which physics principles to apply to be able to solve a problem. So in the physics HSC, formulae are provided on the data sheet. So the questions aren't meant to be testing you on whether you remember the formulae. They're testing whether you can apply the correct formula, and that is problem solving. So I'll give you an example. So motion is modeled by 3 Suvat equations, they're called, and these equations essentially link a few physical quantities, including displacement, initial velocity, final velocity, acceleration, and time. But each of the formulae is missing one of the physical quantities. So if a student has developed their problem-solving skills, then they will be able to look at the question, see what things are given. So maybe they might give you the acceleration, the initial velocity, and the displacement, and they need you to find time, for example. So a student who has developed their problem-solving skills will be able to look at that and select the correct formulae so that they can formulate a very efficient solution. And problem solving is also very important for the ASOEs and the Olympiads. So in the recent years, there's been a trend for the ASOEs to be testing whether students can apply the physics concepts rather than whether they already know many physics concepts. So, I mean, that might seem a bit vague, but what that essentially means is that sometimes in the exam, they won't necessarily expect you to have seen the concept before, but they will provide information about these concepts. And then it's up to you to use your physical intuition to solve the problems. And there's also been times where they've given you a scenario or simulation and asked you to design an experiment, which requires you to use your working scientifically skills. The ASOEs are trying to reduce like the knowledge barrier, I guess. At Toplogic, we believe that students have the best chance of success if they're exposed to a wide range of topics before they actually sit the exam. So I'll talk about more later, but our Olympiad physics course has been structured to cover a large range of topics from mechanics to waves to thermodynamics and electromagnetism at a depth beyond what is usually asked. So whilst it's highly unlikely that you're going to be asked on every single one of these topics, what we want to do is help students develop their physical intuition so that if they see something in the actual exam, hopefully they won't get too stressed and you'll be able to better respond to the question and increase your chances of success. So in the HSC, there has been an extended response in every single year. And there's been at least one 9-mark response every single year from 2019 when the new syllabus was introduced to this year. And this response typically involves both qualitative and quantitative analysis. And over this time, the questions have been tested on every single module. In these questions, they will always provide a stimulus, and it's highly unlikely that they will ask one without a stimulus, because the purpose of these questions is twofold. First of all, they're testing your knowledge of and understanding of the course content, but they're also testing your working scientifically skills, and they're doing that by giving you stimuli which they want you to analyze and process and extract all the information from. So these sorts of questions are marked holistically, and as a result, you need to communicate your response very logically and coherently. So what this means is that you need to be planning your response. You should be using subheadings to categorize your ideas into logical sections, and sometimes it might also be better to use dot points than writing many paragraphs. And communication might just seem like something that is there to help the marketer to understand your ideas better, but it's actually very important because communication is one of the working scientifically skills. So it's sort of inherent in the physics course that you need to have good communication skills. And since they provide a stimulus, you need to analyze all aspects of the stimulus. So I'll give an example. So this question here is from the 2020 paper, and what they asked you was to analyze the motion of the magnet by applying the law of conservation of energy. So you should look at what they give you. So here we have a graph of the distance over time, and we also have quite a few physical quantities. So we have the mass, 0.04 kilograms. We have the height that it falls, 0.78 meters. We have the height of the copper cylinder, and they've told us that it's copper. So you need to be looking at these things and like thinking about it critically and asking yourself, why have they included this? Because in these sorts of questions, they don't just include like the mass of the strong magnet for no reason. Like they've added it there because they want you to calculate something using that value. So for example, in this question, they've given you a height, they've given you a mass, and they want you to talk about conservation of energy. So what I would be doing is calculating your potential energies, because that is something that you can do given what they've given you. And they've also given you the distance time graph. So, and using that, you can calculate velocity. So using that information, you should be calculating your kinetic energy. So you should be looking at the stimulus critically and thinking, is there anything more I can calculate or explain based on what is there? Because if there is more, then you should be adding it to your response. Otherwise, I think it's incomplete. And if it is 9 marks, you don't want to be risking it and just trying to get the bare minimum. You want to make sure that they don't have any doubt that your response deserves full marks. So in physics, we use models a lot. And models essentially what they are is that they're representations of something more complex. So you might have mathematical models to describe motion, for example. You might have models to illustrate concepts like the structure of the atom. And it's important that you not only just know about the different models. So some of the models that you learn about are the atomic models, which you can see there. You have the Rutherford model, and then that evolved into the Bohr model and later the Schrödinger model. So in this case, you don't want to just be knowing about the features of each of these models. The better students will be able to discuss how these models are applied and the evidence used to validate them. So in doing that, you need to be aware that models are inherently limited as they require assumptions and simplifications. And the syllabus is increasingly trying to test this area. So it's very important that you look at these models critically and think about whether in practice, the assumptions that underpin these models have been fulfilled. Because if these assumptions are not valid in real life, then you should not be using the model. Another part of the HSC Physics course is the section on the history of physics. So this mainly appears in Module 7 and Module 8. And in these dot points, generally what it's asking you is that you need to know about a few historical experiments that have contributed to our modern understanding of physics. So within each of these dot points, you first of all need to know what the evidence is. So the actual experiment, the setup, what they found, and you also need to know what it tells us about physics. And that second part is very important. So I'll give you an example. In Module 7, you learn about special relativity, and there are 2 dot points. One of them is asking you about the evidence for the postulates of special relativity, and the other dot point is asking you about the evidence for time dilation and length contraction. So that's the consequences of special relativity. And a very common mistake students might do is that they'll just remember one evidence for special relativity more broadly. So for example, they might remember the muon paradox, which is essentially saying that we observe a lot more muons close to the Earth than we would expect by classical physics, which is a piece of evidence for time dilation and length contraction. But if the question asks them about the postulates of special relativity, some students might still use the muon paradox piece of evidence, even though it's not proving that. So, and in that situation, they're obviously going to lose marks because they haven't provided evidence for the postulates of special relativity. They provided evidence for something else. So it's important that you not only know what the historical experiments were, you also need to be able to remember what their implications are for physics. We also tell our students that it's it can be beneficial to link the historical evidence to physics concepts that you already know. So here I have a diagram of Galileo's attempt to determine the speed of light. And basically what he did was he shone a lantern across a small distance and then timed the amount of time it took for the light to travel. In practice, it didn't work, but I'll just use this as an example. So in this case, this is essentially what Galileo has done, is that he knows the distance, he's measuring the time, and he's calculating speed using the principle that speed is distance divided by time, something that you probably already know. And so in this case, like what I've done is I've linked this experiment to a concept that you already know, and that should help you remember it if they were to ask you a question about it and you needed to describe it. And just for completeness, there are also wave methods. So it's not like every single method out there is getting light, measuring a distance, and measuring the time it takes for it to traverse that distance. So yeah, just try to link the history to what you already know, and that should help you better understand it and better articulate it as well. So I'll go through quite a few common mistakes people make in physics exams. So one of the really big ones and I've done this probably too many times, is that you forget to include units or the direction. So whenever we have physical quantities, we always need to be using units, because if we don't do that, then it's meaningless. Like if I just give you a number and tell you it's a length, like if I say that this table is 8, like I'm not telling you like the unit, and as a result, it could be 8 meters, 8 centimeters. Like you're not conveying you're not conveying the measurement effectively to the marker. And with vectors, they have directions. So things like displacement, velocity, you need to include a direction. So maybe 4 meters north. It's also very important, and Krui touched on this, that you report answers with the correct number of significant figures, because if you don't do that, if you're say you write down exactly what you get on your calculator, like 9 significant figures, then you're not indicating to the marker that you understand the concept of precision. The fact that if your measurements aren't 9 significant figures, then it's useless to write the result of the calculation as 9 significant figures, because you don't even know what the actual value should be that many significant figures away. Whenever you're writing explanations, it's very important that you link cause and effect, because explain means relate cause and effect. So if you haven't clearly linked those two things, then that gives reason for the marker to deduct marks. And it's also important that whenever they give you stimulus material, that you refer to it. And I think I've already talked enough about that. And you should be integrating relevant scientific terms in your explanations where possible, because once again, communication is one of the working scientifically outcomes. Whenever you're doing calculations, it's always important that you do full working, because if in case you make a mistake, if you have working, you actually can get marks if you substitute values into correct formulae. So you want to make sure your working is there, so you can maximize the number of marks you get in case you make a mistake. It's also very important that you understand the difference between accuracy, reliability, and validity. Because if you don't understand the difference between these, then you can't effectively evaluate a scientific investigation. And these are the sorts of things that we cover in the working scientifically lesson at the very start of the year 11 course, so that you're not making these mistakes into year 12. It's also important that you familiarize yourself with the data and formula sheet, because if you don't do that, then you might end up deriving things that are already given to you. And as you could probably expect, that's just a waste of time, because if it's given to you, then it's a sort of like a fair base level where it creates a fair playing ground where everyone can use those, and you're not expected to derive those from first principles. And finally, you should be using diagrams, because they can be a very effective way of communicating concisely. And a lot of the times, a diagram might communicate something a lot quicker and a lot more clearly than if you wrote paragraphs and paragraphs of information. So now I'll talk about the courses that we offer in physics at Toplogic. So like what we have in chemistry, we have an enrichment program, which is more geared towards preparing students for the ASOEs, the Olympiads. And we also have a preliminary and HSC Physics course, which is more for school physics. So like in chemistry, physics is made up of 8 modules, which are split across year 11 and year 12. So that's a total of 7 school terms. And modules 1 to 4 are your year 11 content, and modules 5 to 8 are your year 12 content. But it's important to note that modules 1 to 4 are assumed knowledge for modules 5 to 8. So what that means is that NESA can actually ask you questions about content from modules 1 to 4 in the HSC exam, even though it's not explicitly tested. And generally, they're not going to be asking you about a very nuanced point in one of those modules. It will be things like in module 2, for example, you learn that about Newton's laws, and they might want you to apply that to a mechanics problem, which would come under module 5, advanced mechanics. So it's very important that that you have built a very good foundation for modules 1 to 4 before you proceed into the year 12 course. And that is why we've developed the Toplogic course, because of the fact that our course is accelerated, we have a little bit of time between year 11 and year 12 for you to revise those modules 1 to 4 to make sure that you're in good stead for year 12. So here is the course schedule, and it's pretty much the same as what we have in chemistry. And once again, I won't repeat too much of what Roy said, but the point of this is so that when you're in school, you will have already seen those concepts and you'll be able to better utilize that time to consolidate your understanding and look at new problems. And also just note, the Year 12 trials are generally week 3 or 4 of term 3. So we'll make sure that we've covered all content by then, because as you can see in the diagram, we finish module 8 at the end of term 2. So that gives a few weeks for students to revise before they sit those exams. And it's also worth noting that some schools don't test module 8. So if you're in one of those schools, then I guess that's less content for you. But if your school does test module 8, we will cover it, so you'll be prepared. And as I've said before, we will be embedding working scientifically in the homework across the entire course and with some classroom activities as well. So you should have developed those skills by the time we get to the HSC. So once again, the enrichment program is meant to prepare students for the ASOEs, and I won't talk too much about it because I think Rui has already done a good job explaining what it is and why you should do it. Just replace chemistry in what he said with physics, and that's my talk here. So in terms of the Physics Olympiad topics, you can see here I've color-coded them so to show how they map very well to the HSC course. So in the enrichment course, we look at working scientifically, which is something that you need for HSC, which I've talked a lot about today. We cover mechanics, which is heavily linked to module 1, 2, and 5. We cover waves and thermodynamics, which is what you have in module 3. And we cover electromagnetism, which is what you have in module 4 and module 6. So I think a question that you might have is, if I'm learning all these things in the enrichment course, then wouldn't it just be the same when I get to year 11 and year 12? Does that mean that there's no point in taking both the enrichment course and the year 11 and year 12 courses? Well, the answer to that is no, it's not the same content. Because I think in general, in the enrichment course, what we're doing is we're introducing these concepts more broadly, because as I said before, in the ASOEs, they're not testing whether you have a very nuanced understanding of all these concepts. They just want you to be able to apply, and they want to test your physical intuition. So as a result, in the enrichment course, we're introducing the concepts more broadly. And then when you get to the HSC, you're applying your knowledge to more specific applications. So for example, in electromagnetism for both the enrichment course and module 6, you learn about Faraday's law, which essentially says that a changing magnetic flux will induce an electrical voltage. However, when you get to the HSC, you look at this concept and you go further. You apply it and understand how this is how things like transformers, motors, and generators work. So you gain that sort of theoretical foundation in the enrichment course, but it's in the HSC course where you really need to apply it and extend your understanding of the applications. So I think that's the end of my talk. Our website is there and enrollments are open if you're interested. So thank you.